Welcome back to our channel Paracetamol Academy. In this part, we're going to continue drug metabolism and phase 1 reaction. This is Gael Elia, a fifth-year pharmacy student volunteering with Paracetamol. This video is divided into two parts. The first part will be talking about the material about phase 1 reaction, and the second part would be talking about example related to these reactions. This figure illustrates what happens to the drug once it enters the body. The reactions in phase 1 are carried by enzyme which can accept foreign compound as substrate. Thus, only in case the drug can bind to the enzyme, it will be metabolized. The enzymes that belong to phase 1 can add polar functional groups to a wide variety of drugs and can unmask functional group which might already be present in drug. Example, we can demethylate a methyl ether to reveal a more polar hydroxyl group, and then a more polar metabolite can be renally filtered. Once the polar functional group has been added, the overall molecule is more polar now and thus more water soluble and more readily available to be excreted when it passes through the kidneys. The enzymes involved are mainly non-specific and seen in the liver as CYP450 or in the gut wall, plasma, and other tissues. For example, we have the amidases and esterases. The drug may have affinity to more than one single enzyme, thus it can have more than one metabolite. Also, the same drug may have different affinities to different enzymes, and if the affinity toward enzyme 1 is higher than that toward enzyme 2, then the drug metabolite 1 will be higher than 2, automatically since the affinity toward enzyme 1 would be higher, thus the metabolite giving from enzyme 1 would be in a higher percentage. Additionally, each type of enzyme is available in different isoforms, meaning in different copies, with minor differences in structure that will lead to minor difference in specificity. Some people will find this question to be tricky. How can the same drug have different metabolites even if it binds to a single enzyme? I will try to recapitulate this question in a different form. If we have only one enzyme and we only have one drug, we can have different metabolites. How is that possible? Because the same drug can bind to the same enzyme in different ways, meaning this drug can bind to a specific region in the enzyme in orientation 1, giving metabolite 1 in a certain percentage. The same drug can bind to the same enzyme but on a different site, yielding metabolite 2 maybe in a higher concentration. And also, the same drug can bind to the same enzyme also in a different site, meaning we have 3 different sites that the drug can bind to on the enzyme. And maybe this one will give no metabolite at all, whereby the drug is not metabolized by that site of action. It is very important to differentiate between phase 1 and phase 2 reactions. Phase 1 reactions are all the reactions that are functionalization, meaning we are adding a functional group. The metabolite may or may not have increase in molecular weight, meaning they can decrease in molecular weight and they can increase and they can stay the same. It's not a rule that they have to increase in molecular weight. Unlike the phase 2 reaction where they are conjugation reaction, meaning we are conjugating, we are adding, and thus whenever we are adding, the molecular weight of the molecule of the metabolite would be increased, would be higher. Now to go back to the phase 1 reaction, metabolite may undergo phase 2 conjugation reaction. After forming a certain functional group, via a phase 1 reaction, it can undergo a phase 2 reaction where the functional group formed would undergo an additional reaction. Onto the functional group, we can add a certain molecule. Also, phase 1 reaction have metabolite where they may be pharmacologically less active or inactive, because when we are doing a functional group, they are most probably more polar and thus less active or inactive. They may also produce toxic metabolites, meaning they are actually active, because only active metabolites are toxic metabolites, and it may activate an inactive drug, whereby we can have a prodrug, meaning a drug that would be activated in the body, and upon a phase 1 reaction, a certain functionalization reaction that will occur will activate this inactive drug into a metabolite that is now active and can perform a certain action in the body. However, in phase 2 reaction, the metabolites are generally inactive and they generally do not produce toxic metabolites. Now to go into the detail of an oxidative reaction. These reactions, how the name indicates, they are oxidative, meaning we're adding an oxygen atom usually. The reaction catalyzed by CYP450 enzyme, which is localized in the liver, can involve oxidation of N, P, sulfur, and other atoms like carbon if the carbon atom is either exposed or easily accessible to the enzyme. Example, the methyl substituent on the carbon skeleton forming OH, then a carboxylic acid, meaning the carbon that had the OH, only one oxygen, the alcohol group, can be oxidized from an alcohol to a carboxylic acid, whereby we have an increase in the oxygen number of a drug. Now, a second type of carbon can be when the carbon atom is activated. In the case of longer chain substituent, the terminal carbon most exposed can be oxidized, meaning the carbon at the end of the molecule, the one that can directly go and attach to the site of the CYP450, can directly be exposed and thus can be oxidized. If an aliphatic ring is present, the most exposed region is the part most likely to be metabolized. This slide further elaborates about what functional groups are involved in phase 1 reaction. What groups of drug that are most prone to oxidation? Most of them would be the N-methyl. When you have an N attached directly to a methyl group, this nitrogen is very likely to undergo an oxidation reaction whereby an alcohol group can be added onto this N atom. Also, the aromatic rings, they are likely to undergo oxidation reaction because they are very functional and they are likely to develop oxidation, as well as the terminal alkyl chain, whereby because of their terminal property, the attachment of this terminal chain to the cytochrome is feasible and can be done easily. That's why the terminal chain would be most prone to oxidation and not the chain in the middle or any carbon in the chain. Least hindered alicyclic rings as well, because they are not hindered, then the feasibility of this cytochrome 450 to enter this ring would be easy. Also, now to go on to the reduction reaction, the nitro NO2, the azo N double bond N, and the C double bond O, these three groups are very likely to undergo reduction reaction. For example, the carbonyl carbon, the C double bond O, can undergo reduction to get a C single bond OH, the alcohol carbon. Now, the two groups more likely to undergo a hydrolysis reaction include the ester and the amide. For example, the ester through hydrolysis can give either a carboxylic acid, where the OR group of the ester would be hydrolyzed into the OH to become from an ester to a carboxylic acid, or it can undergo a hydrolysis reaction to yield from an ester an alcohol. Now, this topic is very interesting, actually, because more than 95% of the oxidative reaction are performed by CYP450. Also, about 75% of all drugs currently used in the market, they are metabolized by CYP450, more accurately by CYP3A4, which is responsible for 35% of the biotransformation reaction. The CYP450 has a broad substrate specificity, whereby it can bind to many drugs, and thus the ability to metabolize different kind of drugs when we swallow them or take them into our body. Also, it has the ability to metabolize xenobiotic. It can play a role in the formation of endogenous substance like the steroids. And the second number is the isoform. The majority of drugs are metabolized by 10 isoform of CYP1, CYP2, and CYP3 families in human. It's very important to understand what drug is metabolized by what CYP form, isoform. We have mainly three isoforms, which I mentioned previously. CYP1, 2, and 3 are the big families in the human body. And we have to check if drug A is metabolized by CYP1 and drug B as well is metabolized by CYP1. We have to check if we can take these two drugs at the same time or not, because maybe the drug A can actually inhibit CYP1. If drug A inhibits CYP1, then drug B can no longer be metabolized by CYP1. If it can no longer be metabolized by CYP1, then it will accumulate in the body, yielding to toxicity and side effects. CYP3A4 has a large binding pocket and can accept large bulky molecules that are neutral. It can catalyze N-dealkylation. For example, if we have an N-methyl, this CYP3A4 can demethylate this N-methyl to yield an amino NH2 group. Also, it can catalyze aliphatic benzylic hydroxylation, aromatic hydroxylation, epoxidation, and many more. CYP2D6, which is a CYP enzyme, very significant because it is mainly involved in the antidepressant drug, and thus the importance of it. It prefers less bulky basic molecule and catalyze O demethylation and dealkylation, oxidation of atom near the middle or end of a molecule. And in the previous slide, I have mentioned why oxidation is mainly made in the near end or in the middle of the molecule. This is because this part of the molecule can actually be easily accessible to the CYP and for that molecule to be metabolized. However, if that atom is in the beginning of the molecule, then it would be very hard for that beginning part of the molecule to attach to the CYP enzyme. Also, CYP2C9 has a strong preference for substrate with acidic functional group. It can catalyze O-demethylation, aliphatic benzylic hydroxylation, oxidation of atom near the middle or end of a molecule, as I have mentioned the reason why. Drug-drug interaction is mainly dependent on three things. The first of them, we have to check our drug, for example, drug A, is metabolized by what isoform of the CYP450. After knowing what CYP450 enzyme is metabolizing our drug. Now we have to check if this CYP450 is altered by drug B. Third of all, we have to check the type of enzyme alteration. If we know now that drug A alters the metabolism of drug B, now we have to know what type of alteration is it. Is it induction or inhibition? What do we mean by induction? What do we mean by inhibition? As the name indicates, if we're talking about induction, meaning we are increasing the expression by increasing synthesis or decreasing degradation of a cytochrome 450. This will result in increased metabolism of substrates. However, if we're talking about a CYP450 inhibition, then we are inhibiting and decreasing the enzyme activity, whereby we will have an increase in the concentration of the drug that was used to be metabolized by this CYP450. The CYP450 in the oxidation of xenobiotic is localized in the smooth endoplasmic reticulum known as ER. The CYP450 is a pigment that with carbon and O, carbon monoxide, bound to the reduced form, absorbs maximally at 450 nanometer. The cytochrome are hemoprotein, thiolates, that function to pass electron by reversibly changing the oxidation state of iron, Fe, in the heme between +2 and +3 state and serve an electron acceptor donor. The P450 is not a singular hemoprotein, but rather a family of related hemoprotein. Over 1,000 have been identified in nature, with around 50 functionally active in human with broad substrate specificity. For microsomal drug oxidation to occur, we require 4 different things. First of all, a cytochrome 450 is needed with the enzyme cytochrome 450 reductase to undergo the reaction, energy in the form NADPH. Also, we need molecular oxygen in the form of O2. 5 steps are required for the cytochrome 450 to mediate the oxidation reaction. First step is that the oxidized P450 will bind with the drug to form a complex. Now the enzyme cytochrome 450 reductase will reduce the P450 drug complex formed in step 1. Then after that reduction, P450 reductase will reduce the molecular oxygen to form an activated oxygen P450 drug complex. Step 4. Activated oxygen is transferred to the drug to form an oxidized product. And step 5 is when 1 molecule of water is produced. As mentioned before, for any compound and drug to undergo a certain oxidative metabolism, it requires 3 major things, otherwise the oxidation reaction cannot occur. First of all, we need the presence of a hydrogen atom to be replaced by an OH. Second of all, the atom needs to be exposed to the catalytic binding site of the enzyme. And third of all, the atom needs to be electron-rich in order to attract the activated oxygen to transfer the hydrogen from a hydrogen atom into an alcohol OH atom. As mentioned in the beginning of the video, in the phase 1 reaction, they are mainly the functionalization reaction. In this functionalization reaction, we have 3 different types, which are the oxidation, the reduction, and the hydrolytic. And as we can see in this figure, the oxidation reaction are the most common phase 1 reaction. In the slide here, we can see an example of an oxidative reaction. First of all, the hydroxylation is the primary reaction mediated by cytochrome 450. Hydroxylation can be followed by other non-CYP450 reactions like conjugation or oxidation to ketone or aldehyde with further oxidation of aldehyde to carboxylic acid to a more polar molecule than that molecule which is more polar can be renally excreted and eliminated out of the body. Hydroxylation of the carbon alpha to heteroatom often lead to the cleavage of the carbon heteroatom bond seen especially with NO sulfur, whereby the NS or oxygen can be dealkylated. We need an available hydrogen on the atom for it to be hydroxylated as mentioned before. That is one of the priority for the reaction to undergo an oxidative reaction. In the figure above, we can see that the arene having an R group with an H will be oxidized into an intermediate epoxide and then into an arenol, mainly in the para position depending on the group of R. If R was a good donating group, then the added alcohol group would be in the para position. However, if the R group was a withdrawing group, for example, like NO2, thus the alcohol group will be added onto the meta position. The aromatic carbon, they will undergo aromatic hydroxylation through the epoxide intermediate known as the arene oxide and then will give the arenol. More about oxidation of molecule with the aromatic moiety, which is the benzene ring. We can have an electron donating group on it, for example, like an alcohol group or the NH2 or a methyl group. These are all donating electron onto the benzene ring. However, the electron withdrawing group are groups like a carbon having a C double bond O, carbon triple bond N, carbon double bond N, or any nitrogen or oxygen that are not directly connected to the benzene and there's a carbon in between. In this slide, the diazepam have two rings, one with chlorine, which is deactivated, and one without chlorine and with no substituent. Compound with more than one aromatic ring, 2, 3, and 4, hydroxylation occurs preferentially at the more electron-rich ring. Chlorine is an electron withdrawing group, making this ring deactivated. To recap, the electron withdrawing group are halogens, for example, like fluorine, chlorine, bromine, and iodine, as well as the C double bond O, S double bond O, carbon with 3 fluorine. As mentioned before, every time there is a carbon in between the oxygen and the nitrogen and the fluorine, meaning the oxygen, nitrogen, or fluorine, they are not directly connected to the benzene, then these molecules would be an electron withdrawing group. If the oxygen, nitrogen, and sulfur are directly connected onto the benzene ring, then this ring would be having an electron donating group. Now, antihypertensive drug clonidine and uricosuric agent like probenecide have not been reported to undergo any aromatic hydroxylation. This is because aromatic rings with deactivating groups are either resistant to hydroxylation or slowly hydroxylated. In the case of clonidine, the antihypertensive drug, there is more than one deactivating group, so it is impossible to have a ring hydroxylation. We have highly deactivating ring, not oxidized at this level. In the case of probenecide, the ring is very much deactivated and will not undergo ring hydroxylation. There has to be a different route. Now with a different example having two drugs, the chlorpromazine and the p-chlorophenol. For the first drug, we have two atoms, the sulfur and the nitrogen. The nitrogen donates electron onto the ring. Thus, the product yielding a metabolite having a para atom to the N would be the major chloropromazine product. However, the metabolite giving a para to the sulfur would be the minor chloropromazine product. Now to talk about the drug 2, which is the para-chlorobiphenyl. The para is already occupied because there is a chlorine already formed onto the benzene ring. If chlorine was absent, we would have had two sites for para-hydroxylation into two metabolites, maybe minor and major. However, since the chlorine atom is located onto the benzene ring, then that ring having the chlorine atom as a deactivated ring, and then no molecule and no hydroxylation reaction will occur.